Hi, everybody. Welcome back after a nice lunch and a great morning session. So to kick off our afternoon session, we have a speaker. As I said, it was the second presentation by a winner of a Best Paper Award from this year's, or the most recent NeurIPS conference, the Neural Information and Processing Society. And our speaker is going to be Hassan Ashtiani. Hassan was part of our initial cohort of postgraduate affiliates at Vector. So these are all the grad students and postdocs that are affiliated with Vector. We just ran another round of these affiliates and have a new batch that we're getting set to announce. So Hassan was part of that initial cohort, and now he's a faculty member at McMaster University. And today he's going to be telling us about work about sample complexities and mixtures of Gaussians. And it's worked together with Shai Ben David, who is a faculty member at Vector, as well as a faculty member at University of Waterloo, Nick Harvey, Chris Law, Abbas Marabian, and Yanif Plan. Okay, so Hassan, take it away.
Thank you. Do you hear me? Yeah. Okay. Thank you very much for this opportunity. As it was mentioned, this is a joint work that was presented in NeurIPS. Shai is here now. So let's start. The problem that we want to study here is density estimation, a very well-studied problem where you have samples from a distribution, but you don't know the distribution, and you want to estimate the distribution. And the particular notion of distance that we consider here is L1 distance, which means that you want to find a distribution that is close to the real distribution with respect to L1 distance. What is L1 distance? If you have a simple Gaussian distribution and you mistakenly found the right Gaussian instead of the left one, the error that we say our error will be the area between these two densities. So this is the definition of L1 error between two distributions. And it is a well-studied notion of distance in statistics and computer science, also called total variation distance. So density estimation has been studied for more than a century. And but still, there are many open problems regarding them. Density estimation is used in generative models, in identification problems, so on and so forth. But and a special open problem that still remains is what is the sample complexity of learning a set of distributions? So let's say, for example, you have the class of Gaussians. You know your distribution is a Gaussian. You want to know how many samples do you need to recover the Gaussian. Now, we know the answer for Gaussians. How about for other classes of distributions? This is a resolved problem in supervised learning. We know VC dimension characterizes sample complexity in those settings. But do we have an analog of VC dimension for density estimation? That's the general problem that we want to talk about here. The particular class of distributions that we consider here is Gaussian mixture models, which have been studied for over a century, first by Pearson. And we study them because they are practical, they are very popular, but more importantly, they are building blocks of more complicated distributions. If you can solve their sample complexity, their computational complexity, then you can extend it to more complicated problems. I was surprised 2 years or 3 years ago when I realized that still for such simple models, the sample complexity and the computational complexity is unknown. We don't know whether learning Gaussians is NP-hard or not, or is there a polynomial time problem or not. We didn't know how many samples we need to learn them. So let's start with the definition of a mixture of Gaussian. What is a mixture of Gaussians? Here you have 3 components. Each of them is a Gaussian, and your density is a mixture of those 3. So you have a mixture of 3 Gaussians. And we can also draw the level sets of the Gaussian, which here are kind of ellipsoids, another way of visualizing the data, the distribution. So what you are given is a set of samples from the distribution, but you don't know actually the density function. You just have the samples. And you want to estimate the distribution based on the sample. The question is that how many samples do we need to recover the density among those mixture of Gaussians? So consider all Gaussians of k components. You want to find the best one with high probability. The number of samples will depend on the dimension. Higher dimension needs more points. The number of components and the accuracy that you want to achieve. A technical note that we consider the worst case analysis. We want our sample complexity bound work for every possible Gaussian mixture. Why do we care about sample complexity? Because it helps to design good algorithms as well. If you don't know how many samples do you need, you cannot define, sometimes cannot define good algorithms. So the sample complexity does not depend on the size of the mean, the variance, the condition number, things like that. Okay. So the outline of the talk is that we introduce a new technique for sample efficient density estimation. The technique is generic. It works for different classes of distribution. It's very simple and intuitive. You can use it to prove upper bounds for different classes as well. And in particular, we show that for the class of mixture of Gaussians, kd squared over epsilon squared sample is sufficient and necessary. So we settle the sample complexity of learning Gaussian mixture models with this new approach. But let's start with just a single Gaussian. How many samples do you need to learn that? It is well known in literature that you need roughly the number of parameters over epsilon squared. Here the number of parameters is d squared because the covariance matrix has d squared elements for a Gaussian in d dimensions. So this is well known. But for mixture of Gaussians, we didn't know whether k times d squared over epsilon squared is enough. Again, kd squared is the number of parameters of a mixture of k Gaussians. So it's a very intuitive result, but still open. But where does the challenge come from? Why do we know the answer for one Gaussian, but don't know for mixtures? Consider a different problem. Assume that you have a classification problem, and you have two classes. The left Gaussian is one class, the right Gaussian is the other class. And you want to know which instance is coming from which class. If you look at the decision boundary of this problem, you can see that the decision boundary for these two classes is just a line. It's a simple line. And for any two Gaussians, it could be either line or ellipsoid or, in general, a quadratic form. It's always very simple. Therefore, without going into the details, you can say that because these boundaries are simple, their VC dimension is d squared at most, and therefore you can learn them. You can also do density estimation for just a single Gaussian. But what happens when we go to mixture of multiple Gaussians? The thing is that the decision boundary is not simple anymore. It could be a very complicated nonlinear decision boundary. And we don't know what the DC dimension of this very complex function is. So perhaps you can, if you have ideas, this is a good direction of research because it's still open. But we said, okay, studying VC dimension is not easy here. What if we go and take a more intuitive approach? That's the compression. Consider a simpler problem. You want to learn mixture of 3 Gaussians based on the samples. Okay. In this example, I have assumed that all the Gaussians have unit covariance matrix. Therefore, you don't want to learn the covariance. You just want to know where the mean of each of these 3 Gaussians are. Okay? And the weights are all equal, so the weight of all 3 components is the same. You don't want to learn that either. You generate some points. Let's say enough points, more than 1 over epsilon points. You can show that with high probability, there are 3 points among these points so that one of them is close to the first, the other close to the second, the other close to the third, the center of the third. These 3 points, in a way, can encode the distribution. So you can say, okay, if I had these 3 points, if I knew my centers are close to these, I could reconstruct the distribution so that it could be very similar to the original distribution. In a way, I am saying that a mixture of 3 Gaussians with known covariance can be compressed into 3 points out of 1 over epsilon points. That's the power of compression. So easy, we could compress it into only 3 points. So formally, we say that this class of distributions admits a compression of size 3 and 1 over epsilon, because I have always 3 points among 1 over epsilon points so that they encode the distribution. So let's consider a more general problem for a general class of functions f. We have Alice and we have Bob. Alice knows the distribution, but Bob doesn't. They both know the class of distributions. They have agreed with each other what the protocol is between them. So Alice sees some samples from the distribution and selects only a few and sends to Bob. Bob tries to reconstruct the distribution only based on those points that he received. We say that the class F admits T and M compression if we can always, for any F, in any distribution inside F, we can find T points to send so that it can reconstruct the distribution. So that's the general definition of compression. Why do we care about compression? Because we have shown that if you can compress a set of distributions, then they are easy to learn. Then you don't need many samples. You just need order of the size of the compression over epsilon squared plus m points to learn that distribution. Again, intuitively, if a class admits a smaller compression, it is learnable with less samples. If you are aware of the classic notions of compression schemes in supervised learning, you may observe some connections. So our approach, in a way, is inspired by those from supervised learning, but they had to be very different for distribution learning. Let's also take a look at another example. Here, I want to learn the class of Gaussians, one-dimensional Gaussians. But this time, we don't know mean, we don't know variance. If I generate enough points, then I can show that with high probability, I will find 2 points among the points that I generated from the distribution, such that the mean of these 2 points is very close to the true mean, and their difference, their distance, is very close to square root of variance. So therefore, in a way, again, we compressed single-dimensional Gaussians with unknown mean and covariance to just 2 points from 1 over epsilon points. We can easily extend this idea to mixture of one-dimensional Gaussians. Why? Because you can compress each component separately with 2 instances from the first one, 2 instances from the second one, and 2 instances from the third one. So it's very natural for mixtures. We don't need to prove complicated things here. In fact, we have shown a general result, not just for Gaussians. For any distribution, if you have a method to compress the class, then you have a method for compressing the mixtures of that class. You don't need to prove the result for mixtures every time. Now let's get back to the case of Gaussian mixture models in high dimensions. The only thing, based on this theorem, the only thing that we need to show is that high-dimensional Gaussians are compressible. Then it will automatically mean that their mixtures will also be compressible. How do we do that? Things will be more trickier in the high dimensions. You want to encode not only the mean, but the covariance matrix in a way. And the covariance matrix has d different eigenvalues, and it's not easy to encode them accurately. Our goal is to encode this set of distributions or using only d squared points. Why d squared? Again, because a Gaussian has d squared parameters in its covariance matrix. So, for example, if we have these points, I can try to say, what if I use these 2 points to encode this eigenvector? And for example, these 2 points, the mean of these 2 points can encode the other eigenvector. That would be one idea, but it doesn't work that easy. You may say, why not just discretize the weights or discretize the parameters? You know, one idea, instead of what I told you about using samples to encode the means and parameters, is to use, just discretize all the parameters and send some bits that encode the indices of this mean, the indices of this mean, and the indices of the other mean. The problem is that we cannot do that because don't want to assume that the mean is bounded. So the space is unbounded. You cannot discretize an infinite space. The sigma covariance is unbounded. And even if you assume both of them is bounded, still you have problem when the ratio of eigenvectors in the covariance matrix is high, like this one. Here, if you make a tiny mistake and rotate this contour like only 10 degrees, you will get a totally different Gaussian that does not overlap with the previous one. So the degree to which you want to be accurate depends on the condition number, and it's not easily achieved. The other thing is that we don't exactly want to do parameter estimation. We want to do density estimation, and these are not equivalent in general. Okay? Okay, so anyway, we came up with a method, after all, to encode a set of distributions, a Gaussian distribution in d dimension using only d squared points. Therefore, if we know because it can be compressed, the mixture can be compressed. And because the mixture can be compressed, the mixture can be learned with a few samples. So we showed that these many samples, which is basically the number of parameters over epsilon squared, is enough for learning Gaussian mixture models, improving upon previous works. We also showed a almost matching lower bound based on extended Fano's inequality. Another surprising thing was that when we tried to search the literature, we didn't easily find a lower bound of d squared over epsilon squared, even for a single Gaussian. We had to prove it from scratch, which is the main technical part of the lower bound. So let me summarize. We introduced a new notion of compression to use samples for the compression in the distribution learning setup. This is a very simple and generic. You don't even need to know much about the mathematical details to use this compression framework. And one of the good features is that it naturally extends to mixture models. As an application, we showed tight bounds for Gaussian mixture models. Well, one thing about our analysis is that I said assume your distribution is exactly a Gaussian mixture model, then we recover it. In practice, no real distribution is exactly a mixture of Gaussians, right? So it's not enough to say I have a good method for learning them. We want to assume that the distribution is almost a Gaussian and still be able to recover it, almost a mixture of Gaussian. So we have, after that work, we have extended this to agnostic and robust setting for achieving this result. The other thing is that we showed this for that compression characterizes the sample complexity of learning Gaussian mixture models. How about other classes? Interestingly, for the case of supervised learning, it has been shown that compression is generally equivalent to learning, or it characterizes somehow almost characterizes the sample complexity of supervised learning. Is that the case for density estimation? If someone can prove this, then it will be a huge result. And the last thing is that we still don't know whether a polynomial time algorithm exists for learning mixture of Gaussians. People think it is not possible, but it hasn't been shown yet. Okay, that concludes my talk. Thank you very much.